Hello, my name is Carly Franklin, and this is my submission for Lab 2, Lines of Charge. Introduction. Our goal for this lab is to estimate the charge necessary in a line of charges model to make the bottom tape float. Lab 2 is essentially a continuation of Lab 1, and the charges, instead of being represented by a point charge, will be distributed evenly across the tape, and the model should correctly estimate the amount of charge on each tape necessary in order to make the bottom tape float. Equations are going to be Newton's third law, Coulomb's law, gravitational force, and then I have the resulting charges from each model. For the point charge, it was 1.25 e to negative 8 coulombs, line charges 1.779 e to negative 8 coulombs. And we will go into more of why those values are different later, and assumptions. Okay, this is the glow strip code. We were given a starter code for this lab and told to revamp it to represent our data. So I input my constants, length, mass, distance, all from lab 1. And as you can see, the Q, which I had to edit that line, I got to be 1.779 e to the negative 8. And I will show an image of why that was my charge in a moment. But as you can see, our code has nested for loops for the point charges, which is going to make them all add up, and that represents the vector sum, like superposition lesson that we learned. Superposition for the electric force, how to find electric force when there's many, or representing our line charges model as many point charges together, if that makes sense. And this is the image I was referring to, and this is why my Q, or the charge that I found, was what it was, because I needed the magnitude of the electric force to be equal to the magnitude of the gravitational force, because that is what is causing that bottom tape to float. And the green arrows downward represent the electric field, which will be in the opposite direction of the force because the charge of the bottom tape is negative. So yeah, the green arrow is pointing downwards, but force is pointing upwards, which aligns with our experiment. So what does this all mean? The magnitude of the charge on one piece of tape calculated by my model, 1.779 times 10 to the negative 8. That is a charge required to get those values in the bottom of the image to be equal to each other. And assumptions that were required to make this lab work were to ignore air resistance on a moving object and assume that the U tapes that we had the same amount of charge evenly distributed among the length of the tape. And my last slide, what if ... What if we had modeled each of our tapes as a single point charge like we did in lab 1? Compare the estimated value. Yeah, so modeling each tape as a single point charge overestimated the electric force, which made the charge magnitude smaller than it should be. And with a point charge model, as you can see, I got a smaller charge than the line charge model, just ever so slightly smaller. And these estimations differ because the line charge model distributes charge across the entire tape as opposed to just one location. So as n, which is the number of point charges used to model the tape computationally in the glow script, gets larger. The n I used was 20, but if I made it like 30 or 40, 50, the accuracy of my estimation should get more accurate because I'm adding more separation distances between my many, many charges, and it accounts for the realistic spatial distribution across the charges across the tapes. And the point charge model just has all my charges all accumulated in one spot, which makes my separation distance bigger or smaller. It just makes my separation distance wrong or less accurate, which then influences my value for the electric field. And that is my last slide. Thank you so much for listening.